look at a chord. Now, before we proceed, we need to define a chord. A chord is a line that passes through the center of a circle, or a line that divides a circle into two segments. Now, a chord can pass through the center of a circle. We can have a chord here. We can have a chord here. A chord can run through any line inside the circle. Any line that crosses a circle is a chord. If we label this A, this is B, this is C, this is D, E, and F. AB is a chord. CD is also a chord. EF is another chord. But a chord that passes through the center of circle with center O is called diameter. Diameter, which means that diameter is equal to chord. Diameter is also a chord. So any line that connects the two circumferences of a circle together is a chord. Or a line that divides a circle into two segments, equal or no equal, is also a chord. Now we know what a chord is. Now, the first theorem of circle geometry states that this is a circle, then we have the center of the circle. Let's put another chord here and see what the theorem is all about. Now, this theorem says that when a line runs through the center of the circle and perpendicular to this chord, let's label the chord. Let's call this chord AB. When a line is drawn from the center of the circle, center O, and perpendicular to this chord, is at the right angle. When it is perpendicular to this chord, is at the right angle, which means that this is right angle, this is another right angle. That is, this line that is drawn from the center of the circle bisects this chord. This line can also be called the distance of the circle, the distance of the chord from the center of the circle. So let's label this point. We can label it M. And let's join OB and let's join OA. From the definition or from the theorem, we have AM is equal to MB, since the line OM bisects AB. At the same time, we have that AB is equal to AM plus MB. Also, triangle OMA is equal to triangle OMB. This triangle, this right angle triangle, is equal to this right angle triangle. Now, from this diagram, we see that OA is equal to OB. That is, the length OA is equal to OB, which are what? Radii. So this is radius, this is another radius. Now, from this definition, now we see that this AB, where AB is called length of chord. Length of chord. Length of chord. Let's call it L. So L represents the length of chord, which is equal to what? Which is equal to AB. Now, if AM is equal to, let's say, A, that means A is here. It means MB is also equal to A. So let's put our A here. So therefore, we can say from this equation, we say that length of chord is equal to AM plus MB, which means that let's put our A. This is small letter A plus A. So our length of chord is equal to 2A. So if you know any value of A and we substitute the value, from there we can calculate our length of chord. So let's call this one equation 1. Now let's look at the situation that when this chord AB subtends angle theta from the center of the circle. So if we have the chord AB subtending angle theta from the center of the circle, this is center O, then we have our chord, our radius, we have another one here, radius, then this is the length of the chord AB. So if this chord subtends angle theta from the center of the circle, let's put the distance of the chord from the center of the circle, where we call M. So this is our A, this is another A. This OM is distance of chord from center of the circle. So if you can bisect this theta, it means that this angle will be theta over 2. This one is another theta over 2. That is the meaning. Then, since the two triangles are equal to each other, we can bring out one of the two triangles and see how we can calculate our length of chord from the triangle. This is O, which represents the center of the circle. This point, this is M, and this is B. The same thing applies to this other triangle. Then this is the right angle, that is 90 degrees. Then this angle is half of the angle that we have here. Since the line has already divided the angle into 2, it shows that this angle is going to be theta divided by 2. Theta divided by 2. Now, this is our radius. Then this OM is the distance of the chord from the center of the circle. Let's call it S. Then this is A. Now, from trig ratio, we can say sine theta over 2 is equal to opposite over hypotenuse. From SOHCAHTOA, opposite over hypotenuse. MB is the opposite, OB is the hypotenuse. So we have sine theta over 2 equals to A over R, opposite over hypotenuse, sine theta over 2. Now let's make this A subject of the formula. From there, we have A equals to R sine theta over 2. If you cross multiply, we have A to be theta over 2. Now, let's substitute A into equation 1. We have to substitute A in equation 1. Where is our equation 1? Let's recall that the length of the chord is 2A. If we now substitute, we have length of chord equals to 2. Let's put this is A. Let's substitute A. It's going to be 2R sine theta over 2. L is the length of the chord, R is the radius of the circle, and theta is the angle in which the chord bisects from the or subtends from the center of the circle. Now let's see how we can calculate the distance of the circle, the distance of the chord from the center of the circle. In this figure, we can apply Pythagoras theorem. We can say OB square is equal to OM square plus MB square, where OB is the radius of the circle, which is equal to OM, which is the distance of the chord from the center of the circle, plus A, which is the side of one of the two sides of the base, which is the length of chord. So we have R square equals to S square plus A square. If you make this one subject of the formula, we have S square equals R square minus A square. So if you find x, we have square root r squared minus a squared, where s is OM, which stands for distance of the chord from the center of the circle. That is what this S stands for. Now, this is equation 3. Now, equation 1, equation 2, which is this. This is equation 2. This is equation 2. And equation 3, we can apply it to calculate distance of the chord from center of the circle. We can use it to calculate length of chord. We can use it to calculate radius of circle. Now, if you look at equation 2, this one has to do with radius. If you are given the length of the chord, we can calculate the radius when the theta is given. So these are the 3 equations that we can apply from theorem 1. We can calculate the distance of the chord from the center of the circle. So in our next tutorial, we are going to discuss theorem 2. Thanks for watching.